All right, so imagine you're doodling, right? Just letting your pen kind of wander around the page, making this random squiggly loop.
Yeah.
Could there be like a perfect rectangle kind of hidden inside that mess of lines?
It's a question that might surprise you.
Yeah.
The answer is actually yes.
Yeah.
Every single continuous loop that you draw, no matter how chaotic it looks, hides at least one rectangle within its curves.
Wow.
It's not just like a drawing trick or anything. It's a fundamental mathematical truth. It's called the Inscribed Rectangle Theorem.
That's pretty wild. So today we're going deep into this fascinating mathematical puzzle. We're going to be exploring why rectangles are a guaranteed find, and then why finding a square is like a whole other level of challenge, especially when we get to the world of fractals. And we've got a really incredible four-part explanation that we're going to be drawing from today. It breaks down some pretty complex ideas into really digestible pieces.
Yeah, and what's so fascinating about this problem is that it takes us on this journey through some really core concepts of topology, which is a field of math that looks at the properties of shapes that stay the same even when you stretch them or twist them or bend them.
Okay, so let's unpack this inscribed rectangle theorem a little bit. It states that every simple closed loop in a plane has at least one rectangle with its vertices, or its corners, right on that loop. But how do we even begin to prove something like that? It seems impossible to test every single loop out there.
Yeah, you're absolutely right. Testing every single loop would be an impossible task. But that's where mathematicians get really creative. Instead of trying to test every possibility,
Yeah.
they use this clever technique. It's called mapping.
Mapping, like
Right.
using a map to find our way.
It is similar in a way.
Right.
We're taking a problem, which in this case is about shapes on a flat surface, and we're going to translate it into a different space altogether. So we're going to be mapping pairs of points on our loop to a three-dimensional space.
Three-dimensional space. So we're jumping out of our flat sheet of paper here.
Exactly. Imagine taking 2 points on your loop. The midpoint between those 2 points becomes our x-coordinate in the 3D space. The distance between them becomes our y-coordinate. And then we're going to add a z-coordinate to represent something else, the height of a cake that we're building.
A cake. Okay, now I'm really intrigued. What does this cake have to do with finding rectangles?
So the cake is a visual analogy to help us see how this mapping works. The height of each point on our cake represents the distance between the 2 points on the loop that we're mapping. As we move around the loop and mapping all these different pairs of points, we start to build up this kind of strange, twisted cake shape in 3D space.
So instead of just a flat loop, now we're picturing all these points floating in space with their height determined by how far apart the original points were on the loop.
Precisely. But here's where it gets really interesting. The shape this mapping creates isn't just any random 3D object. It actually forms a very specific surface. It's a Mobius strip.
A Mobius strip. Isn't that mind-bending loop you can make by twisting a strip of paper and taping the ends together? The one that only has one side.
That's the one. And the fact that a Mobius strip only has one side, what mathematicians call non-orientable, is the key to proving our theorem.
Okay, I'm following so far. We've gone from a squiggly loop to points floating in space to now we've baked a Mobius strip cake. But how does any of this guarantee us a rectangle?
Here's the crucial point. A Mobius strip cannot be embedded in three-dimensional space without intersecting itself.
Wait, so you're saying that by mapping our pairs of points into this 3D space and creating a Mobius strip, we're forced to have points collide because the strip itself can't exist in 3D without overlapping.
Exactly. And those points colliding, those are the corners of our rectangle.
Hold on. Let me wrap my head around this. So
Yeah.
because the Mobius strip can only exist in 3D by overlapping, those overlapping points represent two different pairs of points on our original loop that share the same midpoint and the same distance. Therefore, they must form the corners of a rectangle.
You got it. And that's how this mapping trick, by forcing a collision in a different space, proves that every single loop must contain a rectangle.
Wow, that is seriously cool. I never would have thought of it that way. So we've tricked the loop into revealing its hidden rectangle by taking it on this little trip into a space where it's forced to overlap itself. But I have to ask, if this works for rectangles, can we use the same trick to find squares? After all, a square is just a special kind of rectangle, right?
You would think so, wouldn't you? But finding a square is a much trickier challenge. It's not enough for the sides to be the right length. They also have to meet at perfect 90-degree angles, and that adds a whole new layer of complexity to the problem.
So our 3D Mobius strip strategy isn't enough. We need to bring angles into the picture somehow.
Precisely. Mathematicians have explored the idea of adding another dimension to our mapping, an angle parameter, which would take us into 4D space.
4D, things just got a whole lot more abstract.
Right.
But does this extra dimension help us find those elusive squares?
It does for certain types of loops, like circles and ellipses, which are smooth and continuous. In these cases, the angle parameter behaves predictably, and we can find those squares. But when we start dealing with more complex shapes, things get a lot more interesting.
Hold on, don't tell me yet. Let's take a quick pause and we'll come back to those complex shapes and the challenges they pose. All right, so before the break, we were talking about how finding a square inside any loop is a lot trickier than finding a rectangle because we have to worry about those pesky 90-degree angles. And to track those angles, we had to step into this like mind-bending world of 4D space. But you mentioned that this 4D mapping strategy actually works for certain types of loops.
Yeah, for smooth, continuous curves like circles and ellipses, adding that angle parameter allows us to prove the existence of inscribed squares.
Okay, so can you walk me through how that works? I get that a circle is symmetrical, so finding a square inside of it seems almost obvious. But what about ellipses? They're a bit more wonky.
Think of it this way. In smooth curves, the angle of the chord changes gradually and predictably as you move along the curve. So by adding that angle parameter to our 4D map, we can essentially draw a smooth path through that space, and along that path, we're guaranteed to find a point where two chords intersect at a perfect 90-degree angle.
So it's like our 4D map is a treasure map, and that 90-degree intersection is the X that marks the spot where our inscribed square is hiding.
Exactly. Now, in a circle, it's easy to visualize. Any two chords that intersect at the center, if you rotate one by 90 degrees, you automatically create a square.
Okay, that makes sense. But ellipses are a bit more stretched out. How do we guarantee a square there?
Even though ellipses are less symmetrical, that smooth, predictable change in the angle parameter still holds. We can use tools from calculus and geometry to track how that angle shifts as we move around the ellipse, and those tools demonstrate that a 90-degree intersection must occur somewhere. It might be trickier to picture visually, but the math assures us it's there.
Okay, so smooth curves, check. But you teased earlier that things get really interesting when we start talking about more complex shapes. You mentioned fractals. Those infinitely detailed, jagged lines, those don't sound very smooth or predictable to me.
You're right, fractals are a completely different ballgame. That's where the inscribed square problem takes us from a solved puzzle to an unsolved mystery. Fractal loops have this incredible complexity. Their angles can change really abruptly and unpredictably as you zoom in on all the details. It's like every little bump and wiggle has its own personality, making it almost impossible to predict where a perfect 90-degree intersection might hide.
So even with our fancy 4D mapping, those chaotic fractal angles could throw a wrench in the works, making it impossible to guarantee a square.
That's the current thinking, while some mathematicians strongly suspect that every loop, even the wildest fractal, must contain an inscribed square. No one has been able to definitively prove it. It's a problem that has stumped mathematicians for over a century.
Wow, a century-old math mystery. That's incredible. But mathematicians aren't the type to just give up, right? Are there any promising research avenues, any tools or techniques that might help crack this puzzle?
Absolutely. There are some brilliant minds working on this problem from all sorts of angles. One approach involves trying to tame those unruly fractal angles by using polygonal approximations. Essentially, you're trying to smooth out those jagged edges and analyze simpler shapes that get closer and closer to the true fractal.
So it's like building a Lego model of the fractal. We analyze the squares we can find in the simplified Lego version, and then see if those squares persist as we make our model more and more detailed, closer to the real fractal.
That's a great analogy. Of course, the actual math is a lot more complex, but the basic idea is there.
Yeah.
Simplify, analyze, and see what persists as we approach the true complexity of the fractal.
That's fascinating.
Yeah.
Are there any other approaches researchers are using?
Another approach involves using a concept called winding numbers, which is a way to measure how much a curve rotates around a specific point. Imagine tying a string to the curve and then walking around it, counting how many times the string wraps around your finger. It's sort of like a winding number.
So we'd be looking for a spot on the fractal where the winding number indicates a perfect 90-degree turn, signaling a potential corner of our hidden square.
Exactly. And winding numbers aren't just useful for this problem. They have connections to even more abstract areas of math, like knot theory and algebraic topology, showing how a seemingly simple question about squares and loops can open doors to all sorts of fascinating mathematical landscapes.
It really emphasizes how interconnected math is, how one concept can lead to another, and suddenly you're exploring a whole new world of ideas.
Precisely. But let's get back to the inscribed square problem itself. Earlier, we discussed how moving from any rectangle to specifically a square added a layer of complexity that completely changed the game.
Right? That tiny constraint made all the difference. And now we're seeing how the jump from smooth curves to chaotic fractals adds another layer of complexity. pushing us to the edge of what we currently understand about shapes and spaces.
And that's the beauty of it. The inscribed square problem isn't just about finding squares. It's about understanding this deep relationship between shapes and the spaces they inhabit. It's about pushing the boundaries of our mathematical toolkit and discovering new ways to think about geometry and topology.